Welcome to GetX AIML. In this video, we'll discuss about the concept of projection, projection vector and projection matrix and their properties. So these matrices are very important in studying the underlying structure of your systems. Okay. So let's try to understand. The concept looks very difficult, but if you understand, if you imagine it, very easy. Okay. So we'll take some examples and I will make sure that you'll understand it in depth. So let's begin. Here is a formal definition. Projection matrix P maps a vector X belongs to real space onto a subspace W. Okay, what are the items here? There is a matrix equal to the projection matrix. There is a vector X, and then there is a projection subspace. Okay, that is called as W. And then how this looks like X and it's projected on W. You can just imagine this W, the subspace. Okay, and then you have a matrix. When I apply this matrix to X, okay, so X is a some vector. How it maps this onto this W, subspace W. Okay, so this is called as concept of projection. What is the idea here? Technically, you have to understand what is this W, how will you form this W, okay, and how will you form this projection matrix. This is just to take certain form to produce this. So what I am saying, applying the projection matrix X will produce me the projection of X onto subspace W. This is the meaning of that equation. Okay, Px is the shadow or the closest point in W, subspace W to X. It represents how much of X lies in the subspace W. Okay, so that is the formal definition of projection matrix. What is the projection means? Now, we have to understand how this W is formed. What is the W means? How will you get the W? How will you get that P value? Okay, that is what we are discussing here. There are a lot of technical terms involved here. So just look at it. I will explain each terms with a diagram. Okay, this looks complicated, but it's not so complicated. Okay, I will just read out this. Just bear for 1 or 2 minutes. I will explain details. What they say, these concepts you all learned. So if you have missed the concept of subspace, column space, basis, linear independence and all those things, please go back now only the previous videos and just watch the concepts and then come back to this video. Otherwise, it's difficult to understand this concept. Okay. So what the technical definition says, if subspace W is spanned by columns of V, okay, say V1, V2, Vk, there are the vectors in the column space of V, then P is given as like this. What it means, I'll explain it. So here V defines the basis of the subspace W. How the W is formed? W is formed as the subspaces. Okay, W is the subspace formed using the basis of the column space of A, V. Okay, the matrix is V here. Okay. Now we'll come back to other points. First, let us understand this point. So what they are saying. Okay. Let us say this is my subspace W. W is the subspace where the projection happens. And let us say we have a line. A line, say let us represent it as X. Or you can say a vector X. Now, I want to project this using the projection matrix P. Projection matrix P. What exactly it means when I project this? I project this X using projection matrix. Okay, the projection is on this subspace V. Okay, now if V means what? Someone has to form that W, right? Someone has to form this W. So what is this W subspace? W is given as W is nothing but is equal to the column space of vector V. Okay, let us say there are vectors V is equal to say V1, V2, say Vn vectors. Okay, now you already know what is the column space of V. How will you find the column space of V? This is nothing but I will write W equal to column space of V means all those vectors which are linearly independent form my basis of, okay, or span my column space V. That is the definition. The basis already you know. How will you find the basis and how will you find the column space and what is the span? That's why I asked you to go back to the previous video. So there is a vector, okay, V containing the set of vectors, okay, not a vector space V containing these vectors. Now this column space of V, how will you write? So we will write it as W is equal to column space of V. How you find the column space of V? It is the basis of, okay, span of these vectors. It means what? I will take only those vectors which are linearly independent. This forms my W subspace. The subspace is the column space of V. Okay. Now let us assume there are some vectors. Okay. There are some vectors in this column space of V. That is, this is one vector, this is another vector, this is another vector. These are my vectors, say V1, V4, whatever. We are in the column space of is equal to column space of this vector space V, that is subspace. Okay. What exactly this means? The projection onto this subspace. So W understand what is subspace. So when I project this using the matrix P, so I have some projection. That means what? This X, line X, will be put onto this say subspace, this line. Okay, this is a projection of X to W, this vector. See what exactly it means? This projection is mapped the some part on this vector V1, some part on this vector, some on this vector, some on this vector, some on this vector. Okay, there is nothing on this one. So that is what we are finding, on which vectors in the column space this line is being projected. These vectors form my image or the shadow of this vector X. So how will you calculate from this column space of V? How will you calculate this projection matrix so that this setup is formed? This is called as the concept of projection. So technically that is what they are saying. Okay. So now how will you form this? You will form this as P is nothing but V, vector space V, or we can call it as a V is a matrix, V into V transpose, and then inverse of it into V transpose. So this is equal to P. So if you using this vector space, if I form combination like this, then I will get the projection of the, will create a projection matrix for this subspace. That is the meaning. So they both are not independent. See, whatever column space is W, so that is subspace. From that subspace, I want to map, in that subspace I want to map this X. Okay, so how can I find this P? P should be also using this vector space only, right? Because everything this is in my vector space V. So this is how you find the projection matrix. That is what the technical definition is given here. So what are these terms? This V transpose into V adjust for the any non-orthogonality between the basis vector, and V transform measures how much of X lies on each Vi. Each Vi means here this Vi. Okay. Okay. Hence P projects any X into the space spanned by columns of P. That is the basis of this. Is the meaning. This is how, what is the concept behind it. Okay. We'll come back to this figure again. Now we'll see the properties of projection. So it follows the idempotent property. Idempotent property means you already seen P square is equal to P. So if I multiply P matrix 2 times, I will get the same matrix back. So in my previous video, I explained this concept, what this projection means. Why it is P square equal to P, because what it means, if I take a projection matrix P and then apply it, I will get a shadow, that is image. Then even again, if I apply the same thing, I will get the same shadow. So there is applying 2 times projection on same vector will give me the same projection only. There will be no change in the projection. That is the meaning. Then P transpose equal to P. This is symmetric for orthogonal projections. We will come to that later. Then very important are eigenvalues are either 0 or 1. In the orthogonal matrix, we define determinant. Okay, there also you can calculate eigenvalues. There the importance was for determinant. Here for eigenvalues. We will see it later. Then rank of P, this projection matrix equal to dimension of the W. Why? Because see, you already shown it. This is nothing but dimension of W is nothing but what? Column space of V. So therefore, number of independent columns will give me the number of, that's the rank of this projection matrix. I minus P, that is identity matrix minus the projection, projects to onto orthogonal complement of this subspace. What exactly this means? Okay, now these are my vectors. Okay, in the same plane, in the same subspace W, these vectors v1, v4, v5 will also have some orthogonal vectors. Say in the same subspace, say there are vectors which are perpendicular to them. These vectors are perpendicular to them. So this is say v9, v10, v11. Okay. So once I get the projection on say v4 and v4 and v10 are perpendicular to each other. That means what? Can project this X on this also. No, that is the meaning. So X can be projected here also because they are perpendicular to each other. Such a space, we call it as W orthogonal complement. W orthogonal complement means W equal to column space of E. So W orthogonal complement, these vectors which are perpendicular to these projection vectors. Okay, hope you are getting it. So this indicates orthogonal complement. That's what this is. How will you get this orthogonal complement? You will get it by doing I minus P. If I do I minus P and project this X onto this, I will get it on orthogonal complement of your subspace W. That is the meaning. So for this, the projection will happen on orthogonal complement of W. So projection will be like this for this. Hope you are getting it. So let us take an example. So there is a X given here, vector X equal to 1, 2, 3. Project this onto the line spanned by this. Okay. So first you have to find the projection matrix. So using the line spanned by this. So this is the column space of your vector. Now, how will you find P? P is equal to P into V transpose inverse of this, then V transpose. In short, I can write this as, I can bring this to denominator, no? V into V transpose V. V transpose into V. Inverse this. Okay. This I can write it as V transpose into V. What is V here? V is 1, 1, 1. 1, 1, 1. Transpose of this is row vector 1, 1, 1. Multiply these two divided by V transpose, that is 1, 1, 1 into column 1, 1, 1. So this is equal to what? We'll get it as, so this will be a 1, 1, 1 matrix 1, 1, 1 divided by this will be 1, 1, 1 into 1 plus 1 into 1, 1 3. This is my projection matrix P. This P is equal to 1 by 3, 1, 1, 1. I have found out the projection matrix. I want to find the projection using this projection matrix of this vector x. How will I find the projection? I can write it as P into x, right? Applying projection matrix over this x will give me the projection of x over my w. So 1 by 3, 1, 1, 1, 1, 1, 1, 1, 1, 1 into, what is x? 1, 2, 3. So if you multiply this, I'll get 1 by 3. This is go into column. So 1 plus 2 plus 3. This is also 1 plus 2 plus 3. 1 plus 2 plus 3. This will be 1 by 3 into 6, 6, 6. So it is nothing but 2, 2, 2. This is the projection of this x onto this line spanned by V. Now you have to understand. The numerical example. Same concept, the numerical example I have given. So they are saying P, you have to found out P using this P they have given, and you also calculated the column space. And then because there is only one vector given, so you didn't calculate all those. You didn't check for linear independence. If there are many vectors they are given like V1, V2, V3, then you have to find the basis of it. Next. You also already know what is a symmetric matrix. Just a recap. So if the matrix A transpose equal to A, then it is a symmetric matrix. What exactly it means? The entries are mirrored across the main diagonal. If it is A, B, C, C, it will be same. So across the principal or main diagonal, there is a mirror image of this C and C. Orthogonal and symmetric matrix. So you already know definition of orthogonal matrix is Q transform into Q is equal to I. And you know the definition of symmetric matrix. Q transform equal to Q. If both are true, then we call it as orthogonal and symmetric. So properties, so Q square equal to I, because Q transpose is Q only. So if I put Q here, it will be Q square equal to I. Eigenvalues are either plus 1 or minus 1. Q inverse equal to Q because of the property of this. Q into Q equal to I means Q equal to Q inverse. Such matrices helps us to represent reflections across subspaces. The projection is different, reflection is different. Now, reflection across x-axis. Let us take an example. What it means. So Q equal to 1, 0, 0, minus 1. This is nothing but, if I say this is x, y, right? If I take xy, this is nothing but I am saying x equal to minus y, okay, or y equal to minus x. Q is both orthogonal and symmetric. So see here, this is symmetric, and how will you check orthogonal? A dot product should be equal to 0, that is 1 into 0 plus 0 into minus 1 equal to 0. Hence they are orthogonal and they are symmetric also. What exactly it means? It means reflects a point across the x-axis. So this is my x-axis, y-axis. This is negative. This is minus y. Negative y-axis, positive y-axis, positive x-axis, negative x-axis. So this matrix, if I apply, it will reflect y equal to minus x. That means on this. Okay. So eigenvalues. What are the eigenvalues for this? If I calculate 1 minus lambda 0 0 minus 1 minus lambda is equal to 0. Lambda minus 1 into minus of lambda plus 1 equal to 0. So this is lambda equal to plus or minus 1. Okay, what exactly means? Eigenvalues are 1, no change along x. Okay, and minus 1 flip along y. So that's why I am getting the image here. There is no change in the x. It's called as a reflection. X. So for example, here, so y will be giving the reflection of this x here. That is the meaning. Similarly, one more example. Q equal to 0 1 1 0. So Q is both orthogonal and symmetric. Because 1 into 0 into 1 plus 1 into 0 is 0. So orthogonal and symmetric. So have a mirror image here 1 1 along the diagonal. Reflects a point across the line y equal to x. This is C, y equal to x. So this is say x, this is y. So this will be y, this is x. So same again, eigenvalues will be plus or minus 1. This again reflects a point across line y equal to x. So this line y equal to x is like this. Okay. So this, so there is area here. If the point is here, you get one reflection here. That is the meaning. When you apply this to problems, you'll understand it. Any matrix that is both orthogonal and symmetric represents the reflection across some subspace. Direction corresponds to eigenvalue plus 1 remain unchanged. Direction corresponds to eigenvalue minus 1 or flip mirror. Okay. Now, this is again a recap. When we saw the orthogonality, a set of non-zero vectors that are mutually orthogonal is always linearly independent, because we say that this is vector v1, this is vector v2. They are orthogonal, means 90 degree. So they are definitely linearly independent because there is no parallelity between them. So in that case, you already know the condition. How they will help in solving the system of linear equation is the question. So check the orthogonality. So transpose of each vector multiplied by other vector should be equal to 0. Here not all are orthogonal, hence independence cannot be concluded directly. However, there are some methods. So they are not part of your syllabus, then we'll just skip them for the time being. Now we'll see how using the orthogonality condition we can solve the system of linear equations. This is very important. Let for a set a system Ax equal to B, if the columns of A are orthogonal or orthonormal. Orthonormal means orthogonal and the length of each column vector is 1. So can be found independently as, so xi can be found independently as ai is a column vector, transpose of it into the b vector, ai transpose into ai for each column ai. So only thing is what? But to check if the given matrix is orthogonal, then you can directly find the solution like this for Ax equal to B, non-homogeneous system. Let us see this example. A equal to 1 0 0 2 and B is a vector 3 4. They are saying Ax equal to B. That is 1, 0, 0, 2, and say x is x1, x2 is equal to 3, 4. Now, if I find x1 and x2, that is, you have to solve for x1 and x2. If they are orthogonal, then I can directly solve it like this. First, check this matrix is orthogonal. How will you check orthogonal? The dot product should be 0. 1 into 0 plus 0 into 2 equal to 0. So, it's orthogonal. If it is orthogonal, how I can do it? So, x1 is equal to, let us say this is column 1, that is vector a1, this is vector a2, this is my vector b. So what is that you have to do? X1 is equal to ai means a1 transpose into b divided by a1 transpose into a1. What is a1 transpose? So a1 is 1 0, transpose of it is 1 0, row vector, into b. B is a column vector 3 4, divided by again A transpose into A1. What is A1? A1 is 1 0. This is, you see here, 3 plus 4 into 0 is 0 divided by 1. So the solution is x1 equal to 1. Similarly, x2 equal to A2 transpose into B divided by A2 transpose into A2. This is A2 transpose. So 0, 2 into B is 3, 4 divided by 0, 2 into 0, 2. So this we will get it as 8 divided by 4 is 2. That is the solution. Okay. If it is orthogonal, definitely you can solve it like this. So thank you for watching. In the next video, we'll solve few problems on this. Okay. Please like, subscribe, and share.